All right, guys, so in this video, we're going to be looking at some different ways that we can actually measure pressure. All right. Now, the first one here is called a manometer. All right. Now, take a look at what the manometer is. Usually, this section that shows what's being measured, usually that will be connected to some kind of container or whatever, and we're going to be measuring the pressure that's inside that container. Right? Now you can tell by looking at the manometer that we're going to be comparing that to the outside pressure. Okay? Now this could be just open to the outside. It could be connected to something of known pressure. Okay? But hopefully what you're recognizing is that over here on the left side, we have the pressure that we're trying to measure. And then over here on the left side, we have that known pressure. And so what we're going to be measuring is the difference between those two pressures. Now remember, this is called the gauge pressure, all right? Now we can get the absolute pressure. The absolute pressure we can get just by using the gauge pressure and adding that P naught onto it. But initially what we're going to be getting here is just the gauge pressure. What's the difference between the pressure over here that we're trying to measure compared to the outside pressure? And the difference is going to be this right here. Okay, whatever that height is, you've got a delta H there. That height of fluid is going to be the difference in pressure between what's inside and what's outside, right? Remember that at the same height, the pressure must be the same. So if I'm at this height right here, the pressure must be the same. So if we're assuming that this is pretty, this is not very dense, whatever this fluid is in the area that we're trying to measure, then basically this pressure right here of P needs to be equal to the P naught plus the pressure due to that height there. And this is exactly what we've talked about before, which is that P naught plus rho GH equals P. And so using that, we can measure the pressure of whatever's inside of this section over here, just by measuring the height. All right. Now, let's look at another one. So our next way to measure pressure is something called a barometer. Now, a barometer is actually, you often hear barometric pressure. That's how they usually measure pressure when we're talking about weather. And so when you're talking about the air pressure, we're very often referring to a barometer. Now, one thing with the barometer is that a barometer up at the top here will have a pressure of 0. Now, what that means if the pressure is 0 is that the pressure outside is going to push down on the fluid, and then the pressure inside, since it's 0 here, this pressure at this level right here has to be the same everywhere, right? That's what we learned in our previous videos. So whatever the pressure outside is, pushing on the fluid right there, has to be equal to the pressure due to the depth of the fluid right there, which again is our rho GH. Now, hopefully that makes sense, that you then have those two pressures which have to be equal. Again, all we have to do is measure then the height of the fluid inside our barometer. Now, one of the most common types of pressure units actually is something called mmHg. And 1 atmosphere is about 760 millimeters of mercury. Now, the reason why they use millimeters of mercury is because mercury is very dense. And you'll notice right here that this is 76 centimeters. What is that? Well, 76 centimeters is 760 millimeters. And so a normal 1 atm pressure is 760 millimeters of mercury inside of this tube. Now, why would they use mercury? Well, mercury is very dense. Mercury is very dense, which means that it doesn't have to go very high. Because the rho is a larger number, then the height for a given pressure can be smaller, right? Now, this does not measure gauge pressure. This measures absolute pressure. Because we start with 0 pressure inside the barometer, we take out all of the air, everything that we can there, and so we're just comparing the outside pressure to that height of the column of liquid there. Now, one disadvantage to a barometer is that a barometer has to be inside the fluid, right? The manometer, we could just kind of hook up to our tank and we could measure the pressure inside that tank, right? Because it just had to go in the one side there of the pipe. This one, the fluid has to be all around it so that it can push down on the barometer there so that it can actually push the fluid up to the top. Now, please do remember that science never sucks. So it's not that the fluid is getting sucked up the tube, it's that the outside pressure, which is higher, is pushing the fluid and it goes up and it's getting pushed up to that lower pressure up there. And it gets pushed up until it is actually exactly the same pressure. All right, so there's our barometer. So take just a minute on your own to try to answer this question. There should be a few hints inside the question. What I have over here on the right is what's called a tire gauge, okay? And you've probably seen one before. You take this end and you put it on the nozzle of your tire, right? Usually your tire, somewhere in the tire, there's one of those little nozzles there where you can hook your pump up to. You just put this gauge and you put the tip of it there right on top of that nozzle right there. And what it does is the air pushes it out, and you can tell by looking at this stick here, which gets pushed out, you can tell exactly how much pressure there is. All right. Now, go ahead, think about it for a minute. Talk about whether this should be measuring absolute pressure or gauge pressure. Now, hopefully you recognize that it is gauge pressure. Now, the first really big hint is the fact that it's called a tire gauge, right? The second thing is when we deal with the tire, the big deal is how much pressure is there inside relative to outside. If I have 1 atmosphere of pressure inside and 1 atmosphere of pressure outside, that 1 atmosphere of pressure inside my tire isn't going to do me any good because I need that tire to be inflated and pushing against the outside air, which means I actually need a higher pressure inside the tire. But what's important is the difference in those pressures. How hard is the pressure inside going to be pushing towards the outside? That's going to deal with exactly how much pressure there is in my tire and exactly how solid my tire is. You can let some of that pressure out. Some of you know very well when you go out into the sand of the desert that you let some of that pressure out. That allows this pressure inside to be a little bit less. The gauge pressure will be less. Yeah, the absolute pressure inside there will be less too, but really what matters is the gauge pressure. You need a certain amount of pressure inside, or you want to release that pressure to a certain amount so that your tire will be a little bit more flat and will be able to grip the sand a little bit better or will not sink as much in the sand. All right, so hopefully you were able to figure that out. This does measure gauge pressure. Part of the reason why is because it's being compared to something else, whether it be the pressure outside. Most of these have some type of spring inside. You can look it up on a How Does It Work website or something, but most of these have a type of spring inside that it's comparing it to, and so it is some type of gauge pressure where it's comparing it to the outside pressure there. All right, so hopefully that's interesting, and let's move on to the next one. So here we go with our next question, example number 5. A solar water heating system uses solar panels on the roof, which is 12 meters above a storage tank underground. The pressure at the solar panels is 1 atm. What is the absolute pressure at the top of the tank? And what is the gauge pressure at the top of the tank? Now, first thing I want you to do is try to draw a picture of what's going on here. Go ahead and pause the video, draw a picture, and then check mine. So hopefully you ended up with something like this. So you can see in my picture that I've got the tank down at the bottom. I've got the solar panels, which are 12 meters above that. Now in my drawing, I did include, you can see a pipe going up here, and then it comes up here to the solar panels. That's where the water gets heated, and then it comes back down this way. If you didn't include that, that's fine. That's not a big deal. All you really need here is you've got the tank, you've got that it's 12 meters, and of course, you've got this thing here that the initial pressure outside is 1 atmosphere. Now, what I'd like for you to try to do is to find the absolute pressure at the top of the tank and the gauge pressure at the top of the tank. So go ahead and give both those a try, and then pause the video, and when you start it again, hopefully you'll be able to get the right answer. So here we go. The absolute pressure is equal to the ambient pressure plus rho GH. Now, rho is going to be the density of the water because it's a solar water heating system. So the rho is going to be water, which we know is 1,000 kilograms per meter cubed. G is going to be, we'll go ahead and just use 10 for the G, 10 meters per second squared. You can use 9.8 if you'd like. And we've got the height, which is 12 meters. All right, so let's go ahead and put all of those numbers in. Remember that 1 ATM is 10 to the 5th pascals. So it should hopefully look like this, just as we planned. And when we put that together and multiply that out, hopefully we get an absolute pressure of 220,000 pascals. Now this is in pascals because I did use pascals here, and I used SI units for each of these three things that I substituted in before. So there we go. Absolute pressure, this is part A. Absolute pressure is 220,000 pascals. For part B, find the gauge pressure at the top of the tank. So all I have to do is subtract the ambient pressure, which is that 1 ATM, which again was that 100,000, 10 to the 5th pascals. We subtract that off, and for letter B, we get that the gauge pressure, now I'm going to go ahead and label this with a G, so remember that's the gauge pressure, is 120,000 pascals. And there we go. We've been able to answer the question. Hopefully that's the same thing you got.
All right, guys, let's look at another example. But, you know, while we're in this room, you know, I figure I'd just show off my toys. Okay, so I wanted to show you this. Yeah, it's a Millennium Falcon. It's Legos. Put that together. Look at this. It's even got a little Han Solo with him. Yeah, you can tell he's got the lopsided grin. Yeah, that Han's in. It opens up. Look at that. Opens up. Yeah, pretty snazzy. Now you can go and you can play around inside. It even has some little lasers on here, but I think my kids lost them. But anyway, pretty cool, huh? Yeah. All right. I got a little one too. Here, see? I got a little one too. That one doesn't open up or anything. It's just kind of snazzy. But yeah, that's pretty cool. Anyway, all right, let's do some physics. All right, so you've all done this before, right? You've been sitting in a restaurant, you got your straw, your cup of soda, green soda, probably not green soda, but I wanted something that you'd be able to see. So you put your straw in, you put your finger over the top, and it picks up some of the liquid. How do you know? Well, I can see the liquid right there. I can see the level of the liquid. I can release it, and you see that it all drops out the bottom. And of course you sit there and you do that a couple of times because it's fun and it's oddly satisfying and you just want to keep doing it over and over and over again, even if you never thought about the physics. But guess what? We know the physics now. So let's talk about it, all right? So let's look at the example here. I got a straw with a length of 15 centimeters and a diameter of 4.5 millimeters. A person puts their finger over the top of the straw and draws out a 10 centimeter column of water. So what I'm saying is that I put my finger over the top and I've got 10 centimeters there, all right? That's what we're looking at, a 10 centimeter column of water. What is the pressure at the top of the straw? What does the pressure have to be up here in order for that situation to work? All right, so I'd like to give you just a minute, when I say pause, go ahead and pause the video and see if you can work it out for yourself first, and then see what happens when I work it out with you, all right? Pause. So hopefully the first thing you did is that you took time to draw a picture, all right? So the picture should look something like this. And that's it. Notice my superbly drawn finger there. Just don't ask me to draw a whole hand. Ain't gonna happen. All right, so with this, we should be able to solve the question, right? We know that at a given level, that the pressure should be the same everywhere, as long as it's in equilibrium, right? We do understand that if two pressures are different, then it would not be in equilibrium. But when I have my finger over that straw, right, and I pull it out and I just kind of hold it there, we're basically in equilibrium there, right? So with that, we should then understand that we do have an equilibrium position. Out here, the pressure is just the ambient pressure. Okay? Now, right here, the pressure is going to be the pressure inside the straw plus whatever the pressure of that fluid is. And that's what we're looking for. What's the pressure up at the top of the straw in that
space of air. Now before it was P naught, but it's got to be less than that now, right? It has to be enough that the ambient pressure is pushing up, allowing that extra fluid, that extra water to stay in there. And so the PS has to be a lower pressure than the P naught. And so we can just write this out, right? We can say that the P naught is equal to the pressure inside the straw plus rho g h, right? These two things, pressure inside the straw and then the liquid there. Now we can actually put all those numbers in. We have most everything. If we assume the ambient pressure to be 100,000 pascals, which we will, that's normal atmospheric pressure, then we can find the pressure of the straw. Because we know that the density of the water is 1,000, we know that G is 10, and we know the height is 10 centimeters, which is going to be 0.1 meters. Remember, everything needs to be an SI unit so that I end up in pascals. Now the 10 and the 0.1, those are actually just going to cancel each other out. Subtract the 1,000 to the other side, and I get simply 99,000 pascals equals the pressure in the straw. Now that doesn't seem like a big difference, right? It went from 100,000 down to 99,000, not a big deal. You're right, it's not, but it's enough. That's not a lot of fluid. It's only 10 centimeters of fluid. It's not a lot there. So you just need a very small pressure difference for that outside air to be able to push it up. And so there we go. We know the pressure at the top of the straw is 99,000 pascals. Still a pretty big number. Doesn't need a big, huge difference. And actually that happens because when you put your finger on it, then what ends up happening is that the fluid drops just a little bit. And so it increases the volume up here. And so if this volume, as that fluid drops down just a little bit, it increases the volume, which some of you that have done some chemistry understand that increasing the volume decreases the pressure. Now, if you haven't done that, don't worry. We're going to see that in our next unit. All right? So that's it for now. Hopefully that made sense. And let's see another one. Now let's have a quick chat about my buddy Shyaam. Shyaam is getting really excited about this pressure stuff. All right, so he created a super duper long straw that will reach from the top of his house all the way down to a cup on the ground. And he's going to try to drink some whatever he's drinking, water. We'll just use water just to simplify so we can use that 1,000 kilograms per meter cube. All right, so he's going to try to use his straw to drink from that cup. All right, so what I'd like for you to do is consider, is that possible? Now, the first thing I want you to do is to draw a picture. So think about a picture, what would it look like? And then secondly, see if you can answer the question, all right? All right, so hopefully you drew something like this. You've got Shyaam, he's got a straw, which is 12 meters, and the question is, can he drink from this straw from the top of his house? All right, now that you got a picture, see if you can solve it. So hopefully this is the math that you're thinking through, right? So you're saying that out right here at the bottom, we need the pressure to be the same for everybody. We can do right here at the top of the liquid. That'll simplify it. Okay, so right here at the top of the liquid. So on one side, we've got the atmospheric pressure pushing on the outside. All right, so that's P naught. And that needs to be equal to the pressure due to the height of the liquid. So that's rho GH plus the pressure that Shyaam can create. All right, now let's go ahead and try to figure this out. So the pressure outside we're going to assume is ambient pressure equals the density of the water, 1,000, times G, which is 10, times the height, which is 12, and then plus PS. Now if we work that out, 1,000 times 10 would be 10,000, times 12 would be 120,000. And when we subtract the 120,000 to the other side, we actually get negative 20,000 is equal to the pressure that Shyaam needs to create. Now, that's not possible because we're talking in absolutes here, right? That ambient pressure, which is 10 to the 5th pascals, that's an absolute pressure. So that is relative to absolute zero, which means no pressure at all. Nothing is pushing. So therefore, if we try to create negative 20,000 pascals of pressure, there's no way to do that. You simply can't. Now, if that was a gauge pressure, sure, it could be 20,000 less than something else, but we're talking about trying to make negative 20,000 absolute pressure, which is not possible. The lowest possible pressure is 0. That means nothing, no pressure at all. You can't have negative pressure. So therefore, the answer is no, Shyaam can't use this straw. In fact, there is a maximum length that this straw can have. Now, I give you a challenge to try to figure out what that is. You should be able to do that by using this. If you assume that Shyaam can create 0 pascals of pressure somehow, that he can create an absolute vacuum inside of his lungs when he's trying to use that straw, or even using a specialized pump or whatever he wants to use. If you assume that that is 0 pascals, what is the maximum height that you can have? What's the largest straw that can be used? Now, go ahead and work through it. Hopefully you get 10 meters. I'm not going to work through it here. If you have questions, I'm happy to look at it with you later, but you should get 10 meters. All right, let's move on to the next one. Last one. Quick partner chat. If you can, chat about this with somebody else in your home or that's near you. It could be a friend, it could be a parent, it could be a sibling. But take just a minute and see if you can remember. We did talk about this at the end of the school year, but see if you can remember, how does a vacuum cleaner work? Use as much physics terminology as you can, and see if you can come up with an answer. Draw a picture, do whatever you can. Go ahead, I'll go ahead and pause. You should pause the video, and then I'll go ahead and give you one version of the answer. Pause. All right, so here we go. Let's talk about how a vacuum cleaner works. First thing we're gonna do is draw a quick picture. So, all right, so that's pretty much it. This is the basic idea. You've got a fan inside, and what the fan does is that the fan starts spinning. As the fan hits the air particles, the fan exerts a force on the air particles and pushes them out. So the air particles get pushed out of the vacuum cleaner like that. Now, once you push those particles out, now there's less particles inside of this area, which means that your pressure is going to go down. Remember, pressure is force per unit area. The area isn't changing, but the amount of force is. If there's less particles, they're going to be hitting the side less often. And so we're going to have a lower pressure in there. Now, if we have a lower pressure in there, then what we have is the high pressure on the outside is now going to push in towards the low pressure. High pressure on the outside pushes into the low pressure, and therefore you have a vacuum cleaner. It's all about that high pressure pushing into the low pressure, and that's just that one of those things that naturally happens is the high pressure area is always going to be pushed towards the lower pressure. All right, so that's the basic idea of how a vacuum cleaner works. Go ahead and move on to the next segment of this module.